All right. So what did we do last time? Recall. So we started thinking about conformal maps. F from U to V is a conformal. Again, really conformal means angle preserving, and all holomorphic functions are angle preserving, but we want conformal. Okay. If F is holomorphic and bijective, which means it has an inverse, and the F inverse is holomorphic. That's just the definition. And U and V are conformal if there exists such an F. And then we proved that if F is injective and holomorphic, then the derivative doesn't vanish. And we proved that that implies, so if it's injective, well, its image is open. Image is open, so we can make that. If you had a function from U to some other place, well, it's not reaching anything other than the image of F, in other words, F of U, whatever the domain was. Then, okay, it's bijective on the image, then F inverse is also automatically holomorphic. So this is automatic from this and this, right? Good. Okay. That's what we proved. And we looked at some examples. What did we do? Did we do the upper half plane? We must have. Yes. Yes, we did two examples. Example one was upper half plane to the disk that sent Z to Z minus I over Z plus I, which we could write as 1 negative I, 1 I acting on Z, fractional linear transformation. Example two was the upper half plane to the slit complex plane, where you take out the positive or non-negative reals that take Z to Z squared. Right, so this was how this region folds under Z squared onto remove this, and this part goes here, and this part goes here. And that's as much as we did, right? Okay, so let's get some more examples. Example 3. All right, let's have some fun. Example 3. How about F of Z is equal to 1 plus Z over 1 minus Z on the upper half disk. Let's call this F3. Upper half disk, so I take the disk and the upper half plane, and here's the upper half disk. So what is the image? I don't expect you to know this off the top of your head at all. This is the kind of thing that I want you to be able to figure out. So this is the next bit of technology we're developing. We're developing the dexterity to be given a map, be given a domain, figure out what the range is on which it's bijective. Now, what do you notice? Is this even holomorphic on the upper half disk? Where do we have a problem? Yeah, at Z equals 1. So right there, we're going to have a pole. Well, on the disk, on the upper half disk, we're okay. There's no pole. It's on the boundary that there's a pole, but something's blowing up. So here's a trick. Here's one way to understand all of these so the idea is to just look at the boundary. Look at the boundary of U. What does F do there? F need not be defined there, but where it's defined, it'll usually be continuous if it has a continuous extension to the boundary, which this function is, of course, meromorphic except and holomorphic except at z equals 1. So it has analytic continuation everywhere except here. So it's certainly continuous on the boundary except at this one point. So let's look at the boundary. So this has two boundary components. So what happens to f? I'll call it f instead of f3, but I'll want to use some of these. So let's keep track of this. Was example 3, f3. Restricted to the interval -1, 1. So this is just f of x. This takes a real number x to 1 plus x over 1 minus x. So we're used to graphing these as here's what happens to x. Whoops. Here's what happens to x. Here's what happens to y. That is not where x goes in any sense of the. So here's -1 to 1. And okay, I blow up at 1. I have a 0 at -1. So I'm at 0 at -1. Right? This is like, what, 11th grade? When are you graphing things? Maybe calculus, 12th grade? We take the derivative, we see where there are inflection points, right? There's all this fun stuff. The derivative, all right, what's the derivative? It doesn't really matter what the derivative is, as I'll show you in a second. Well, okay, if you didn't know that f was injective on here, well, the way to figure out that f is injective is to take the derivative. So we need the derivative anyway. So what is the derivative? F prime. F prime is bottom times top minus top times the derivative of the bottom all over bottom squared. And I get the z's canceling and I get a 2 on top. So this is not 0. This is never 0. And similarly, this will not be 0. So it doesn't matter what it is. I just need to see what happens when x is near 1. When x is 0.9, this is 1.9, and this is 1 over 0.9. So anyway, it's positive. So this is going to plus infinity. We have a vertical asymptote, and whatever it does, I don't care what it does something. I have no idea if it looks like this or if it looks like this. I don't care. It has no, the derivative never vanishes, and it goes up. So what that means is f maps the region. So f takes the region -1, 1 to this region -1, 1 gets mapped to 0, infinity. I don't care about what the curve actually looks like. I care what its range is, and its range is 0, infinity. Okay? So one thing we know so far about this example is that this is the beauty of colored chalk. That region going that way, -1, so f of -1 is here, and f of 1 is infinity. And we're staying real. Okay? You guys see that? All right. What about the other boundary? We have the other boundary. So f restricted to, how should I put this? E to the I theta, theta between 0 and pi. Let's see what happens there. 1 plus e to the I theta over 1 minus e to the I theta. Oh gosh, how are we supposed to work this out? Well, there's a trick, which is if we pull out an e to the I theta, let's say from either the top or the bottom. Which do you want, the top or the bottom? Well, okay, let's multiply top and bottom by, how would you think about this? We could multiply the top and bottom by 1 minus e to the minus I theta. 1 minus e to the minus I theta. Okay, this is a 1. What am I doing? I'm multiplying it by its conjugate. This is the conjugate. So I get 1. I get a minus e to the I theta and a minus e to the minus I theta. So I get minus 2 cosine of theta and then a plus 1. Did I do that right? I get a minus e to the I theta. I get a minus e to the minus I theta. So that's a minus twice cosine theta. Cosine theta is e to the I theta plus e to the minus I theta over 2. And then these two give me another 1. Yes? And then what's happening on top? I get a 1. I get an e to the I theta minus e to the minus I theta. I guess that's a plus 2I sine theta. And then minus 1 in the end. Hello? Okay, I don't know why that's happening. Does everybody see that? Is that what you got also? Okay, the 1 and the minus 1 cancel. There are 2's on top and bottom. So I think I'm getting I sine theta over 1 minus cos theta. And so what happens to this? So first of all, it's purely imaginary. Sine from 0 to pi goes like this. This is sine from 0 to pi. Cosine goes like this, just like this, 0 to pi. This is cosine. 1 minus cosine. So minus cosine goes like this. This is minus cosine. And then I add 1 to that. So this is 1 minus cosine. So what's going on? What is going on? It looks to me like this. So the y, let's see, if I put theta here and I put sine theta over 1 minus cosine theta, what am I actually getting? This is a first order 0, and this is a second order 0. And so the ratio will still blow up. So this starts out, so I want to know what's going on from 0 to pi. I claim this is blowing up. And is it blowing up positive? Yes, everything's positive. So this is blowing up. And then what's happening at pi? At pi, sine is 0 and cosine isn't. I mean, 1 minus cosine. 1 minus cosine isn't. So we're going to 0 here. This is 0. So it's some curve like this.
Professor?
Please.
Isn't it cot theta by 2? This sine theta over 1 minus cos theta.
Sine theta over 1 minus cosine theta. What are you saying? It's cosine of theta.
Cotangent of theta by 2.
Of theta over 2?
Cot.
Cot. Cotangent. That seems right. You mean if I multiply top and bottom by 1 plus cosine, for example, then I get a 1 minus cosine squared, and I get a 1 plus cosine on top, and the sine on top and bottom cancel. Something like that?
We've also done the factor the e to the I thetas out.
Or
You
we
can also
can-
factor the e to, that was the first thing that I was going to do,
Cotangent.
and then I thought maybe that was too slick. And so I thought I would try to do it some less slick way. Yeah, okay. Maybe let's do it the slicker way. The slicker way is 1 plus e to the I theta. I'm going to pull an e to the, let's multiply top and bottom by, here's another way of doing this. We need to split the difference. So I'm going to multiply the top and the bottom by e to the minus I theta over 2. That's another trick. That'll have the same effect. So I get an e to the minus I theta over 2 plus e to the plus I theta over 2. E to the I theta over 2. That's a 2. Does that make sense? And then on the bottom, e to the minus I theta over 2 minus e to the I theta over 2. And so now maybe it's blatantly obvious that this will be, well, the top is twice, I still have to do it with cosines and sines, twice cosine over 2, and on the bottom I get negative 2i times sine of theta over 2. So I think I'm getting I times cotangent of theta over 2, which is exactly what, who was it, Rishab? So this graph is a familiar graph, it's just cotangent, great. Great, I agree with this identity. But again, all that matters is we start at infinity and we go to 0. And so what all that matters is the domain, is the range, and the range is 0 to infinity times I. And so what we can say is that this part of the curve, as I go from, let's say, -1 out to here, f of -1 is still down here, and then I go up that way. And I didn't give the arrow for which way that goes. And now I take some point in the middle. So I take some point in the middle, like I over 2. So what's f of I over 2? Here's I over 2. I mean, you can sort of guess where we're headed here. F of I over 2, what's the function again? 1 plus z over 1 minus z. Here, let me zoom out. There we go. 1, hello. Okay, I'm learning to use this. 1 plus I over 2 divided by 1 minus I over 2. How do you want to do this? Let's multiply the top and bottom by the conjugate. 1 plus I over 2. 1 plus I over 2. What am I getting here? 1 plus a quarter. And here I'm getting 1 minus a quarter plus I. So this is like 3/4 plus I. So 3/4 plus I. I don't really care where it is. It's somewhere over here. F of I over 2. And that's it. It's continuous. And it takes this boundary to that boundary. So now we know exactly what the image is. Cool. So
and I guess do we know it doesn't cross back over itself because we know it like has an inverse or something?
It's 1-to-1. Yes, its derivative is non-vanishing.
Oh, right. Okay.
So that's it. That's the map. So F3, the conclusion is that F3 takes this region to this region. Cool. Let's do another one. Any questions?
Wait, so we got from the fact that its derivative was non-vanishing to the fact that it's 1-to-1?
Yes. Well, the derivative non-vanishing is a local 1-to-1.
Right.
And then, yeah, I guess you need to be given the initial domain. When you're given a function, you want to. So, for example, with z squared. I mean, this was this was the question. I forget who. Maybe Ishan was asking last time. With z squared, if you take the disk, so if it's injective, then the derivative is non-vanishing. Z squared on the complex plane minus 0 is non-vanishing, but it's not injective. It's locally injective. In any region, there's a small ball around which it's injective. But then globally, it closes up, and it's exactly 0 that's the problem. There's no neighborhood around 0 that's injective. Does that make sense? Let's do another one.
So after we figured this out, we should show that this is injector maybe?
Yes, if you like. Yes. So, well, one way to show that it's injective is to show that it has an inverse. And so the function, if we think about it as a fractional linear transformation, is this. So this is f of z. It's z plus 1 over z minus, minus 1. It's z plus 1 over negative z plus 1. Z plus 1 over negative z plus 1. And so the inverse is very simple. So f inverse, I just read it off. I switch the diagonals, I negate the off diagonals, and I would divide by the determinant, but we're in PGL2. So the determinant doesn't do anything. So f inverse, so this sends, where does this matrix send? This sends z to z minus 1 over z plus 1. And this is well defined. This is well defined unless z equals negative 1. And z equals negative 1 is over here. So we're outside the region where that inverse function is not holomorphic. Therefore, it has an inverse function. Therefore, it's 1-to-1. Does that make sense?
So could we expand our domain and get some more sets that are conformal?
Yes.
Cool.
Yes. As long as we avoid negative 1, as long as we avoid the place, what goes to negative 1? Well, what am I trying to say? Yes, we can extend the domain. The domain was part of the input. We were given a function and we were given a domain, and the question is, what's the range? But really, this is warm up for the big picture. Will be if I give you two domains, how do you find a function that maps one to the other? Okay, that's the real. I want to show the two things are conformal, so I need to exhibit bijective holomorphic map from one to the other. So this is warm up for that by saying what happens to various domains. I give you functions and domains, not the largest domain on which the function is one-to-one, but just a domain. And can you figure out the range? That's the game. Okay. All right. Example, what number is this? 3, example 4. Example 4. Example 4. Yes, of course, log. Let's do log. So F4 is log Z, by which I mean the principal branch. And I want the domain to be the upper half plane. Want to work on it? Want to take a minute and work on it? Okay. Give me a thumbs up when you know what the domain, what the range is. Is someone saying something or just someone's not muted? Maybe Alex or Kayla? Oh, okay. Give me a thumbs up either when you've got it or you're stuck and you're not computing anything. Thomas, you got it or you got it? Okay. Sriram, you got it? So again, the principal branch means I remove, I'm not allowed to take log on this entire region. Does anyone want to tell me what they're computing? Oh, everybody's hard at work. Okay. Is anyone using polar coordinates? Remember, if you have a point Z here, which is R e to the I theta, and theta is between 0 and pi, then that gets sent under log in the principal branch to what it should be, log R plus I theta. And what's the range of R? R can be as small as you want or as big as you want, right? R ranges from 0 to infinity, and theta goes from 0 to pi. So this is the real part, and this is the imaginary part of the image. So the real part ranges from what happens to the log function on 0 to infinity log r goes from minus infinity to infinity. And I theta just goes from 0 to pi. So what is that? Thomas got it. Yeah, Kailash got it. Okay, great. People are seeing it. Exactly. It's going to be a strip. The real part goes from minus infinity to infinity. The imaginary part goes from 0 to pi. So that's weird. It seems we're getting a strip. How in the world are we getting a strip? Well, if z is just r, then there's no problem defining the branch, right? If z is a positive real number, then its log ranges from minus infinity to infinity. So we're getting the entire boundary, right? Here's 1, log of 1 is 0. So this is f of 1. And if I continue around the unit circle, r remains 1, and so its log remains 0. So this point, -1, it has a theta equal to pi. And so it approaches 0 plus I pi. So this is f of -1. And then by changing r, I change the real part. And so that's the other bit of the boundary. So here's a question. If I put the arrow going that way, which way do I put the arrow here?
The same way.
The same way?
Like parallel.
Why do you say that?
Well, because like we're kind of just translating polar coordinates into Cartesian coordinates.
Yep. Just think about what happens here. At -2, r got a little bit bigger. Well, that means that the log r got a little bit bigger. So that's it. That's the map. We can take the upper half plane to a strip under log. That is what log does on that piece. Cool? Let's do another. Let's do another. Example 4 was log. Example 5. Example 5 is e to the iz. F5 takes z to e to the iz. And the domain, let's take minus pi over 2, pi over 2, and up. So this is z x plus iy with x between minus pi over 2 and pi over 2 and y positive. What happens to that? Sriram, you see it?
Still thinking.
Okay. Bless you, Nick. I guess each one of these uses, I mean, you can do it by the techniques of the previous, like looking at the boundary and so on. But each one of these has a there's a slicker way of doing it. So each one of them introduces a different slick little thing you could do to figure out what the image is, what the range is. So these are all exercises in that. Thomas has got it. Give people another minute or two. Kailash, you got something? Awesome. Should we try it together? Here's how I would do this one. If z is x plus iy, e to the iz is e to the ix, iz, e to the minus y. So the absolute value of this thing, I mean, this is the magnitude and this is the argument. It's in polar coordinates already. So this thing in absolute value, the whole thing is less than 1 because I have an e to the iy and y is positive. So I'm going to be inside the unit disk. And my argument goes from minus pi over 2 to pi over 2, from here to here. Does everybody see that? You just read it off. So let's see if we can see where pieces go to. So what about if we're purely real and we go from minus pi over 2 to pi over 2? Where's that? Does everybody see that? So in particular, where does 0? 0 goes to 1. So this is f of 0. And if we move this way, we get to pi over 2. E to the I pi over 2 is up here. And e to the minus I pi over 2 is over here. Now this is funny. So what's going on in these directions? So we start here and we start here. So this is f of minus pi over 2. And we just increase y. So we keep our argument the same and we just decrease the magnitude until we get all the way to 0 as y goes to infinity. You see that? And similarly, new color. What is this? Hot pink or something. Okay. And hot pink starts from f of pi over 2 and does the same kind of thing. Cool? Let's do another. We're getting good at this. All right, let's do a slightly trickier one. Maybe you guys are getting so good at it. Here's example 6. I want f6 to take z to negative 1/2 z plus 1 over z. Okay? Negative 1/2 e to e, negative 1/2 z plus 1 over z.
And the domain?
I haven't given you the domain. All right, let me give you a domain. Let's see where this takes the disk intersect the upper half plane too. So the upper half disk. If you can do this without computing, I'll be extremely impressed. I mean, I don't know how to do this without computing. You got it, Thomas?
I think so.
Okay, don't tell us yet. People are still. Is there some coded way for you to tell me what it is without revealing it to everyone else?
You can send private messages in the chat.
Oh, that's true. Of course. I'm thinking of some crypto system that we could invent on the fly and have a public key exchange while everyone's computing. No, you can just chat me privately. It's okay if you're wrong.
Let me just check it one more time.
Okay. I see you're doing all of this without writing anything down.
Right. I'm gonna tell you my guess based on that.
Okay. Nice. Should we do it together? Some people are still computing. Some people are now scratching their heads. Anna, what do you think? You want more time or should we do it together?
We can do it together.
Okay, so let's do it together. So where do we have a poll? Where do we have something that's weird's gonna happen, right? I mean, we could write this as z squared plus 1 over z. So it's not a fractional linear transformation. It's not gonna be one of those nice, easily invertible things. Oh yeah, we didn't check that all of these were holomorphic, but for each one you can write down the inverse easily, right? The inverse of log is exponential. The exponential function will take this region to this region. The inverse of this is the logarithm. So the log will take this region with a branch cut to this region. And this we already talked about the inverse. Yes. Yeah, it's not obvious. It's not at all immediately obvious that this one has an inverse, but let's get to that later. So this has a problem. This has a pole at z equals 0. So there's something funny going to happen here. So I think we should, well, let's look at this region first. What happens on here? On e to the I theta, theta between 0 and pi. F of e to the I theta is -1/2. I get an e to the I theta plus e to the minus I theta. So I think I'm getting negative cosine. Is that what everybody else got? So negative cosine is going to go, instead of from 1 to -1, it's going to go from -1 to 1. This is negative cosine. So -1 to 1. All right, so this is going to get mapped to, let's see, what's f of 1? So f of 1, 1 plus 1 is 2. F of 1 goes to -1. Does that seem right? So that's this -1, and then we're going to make our way up to +1 as we go around to here. So f of -1 is actually +1, and it's real. As we move through the disk, we get real. We're just real the whole way. That way. That way. Cool? Okay. And now there's these regions. So, well, we could try to work them out. What happens to the real line? So on x in minus 1, 1, we have f of x is negative a half x plus 1 over x. How do you graph x plus 1 over x? Okay, we have a vertical asymptote. With x is equal to 1, I get, again, negative 1. So at 1, I get negative 1. Well, that's this. And at negative 1, I get 1. At negative 1, I get 1. And then I guess if x is negative, so this has no other choice but to go like this and like this. And so from negative 1 to 0, we go from 1 to infinity. On negative 1 to 0, on negative 1 to 0, we go from 1 to infinity. At 0, we're blowing up. We already knew that. And we're real. Everybody see that? And finally, from 1 back to 0, we go from negative 1 to negative infinity. Cool? And then what happens to, I don't know, I over 2? What's f of I over 2? F of I over 2 is here. F is negative a half. I over 2 plus 2 over I, which is also I over 2 minus 2I. So this is negative 3 halves I, negative 3 halves I, times negative a half, times negative a half, 3/4 I. 3/4 I is here. This is f of I over 2. So we get the upper half plane. Okay, let's do one last one, and then we'll take a break. Is that okay? One last one, example 7. F of z is equal to, you thought you knew this function. You've seen this function your whole lives, and now we're going to see what it actually does. F of z on, let's say, negative pi over 2 to pi over 2. Boom. Now let me give a hint as to what you might want to think about. Hopefully you can see the whole thing now. You shouldn't have to do any work. You shouldn't have to do any work. Sine of z is negative, so it's I times negative a half. Sine of z, as we all know, is e to the iz minus e to the minus iz over 2I, which I will write. I'll move the I up top. So it's I times negative a half e to the iz minus 1 over e to the iz. So in fact, sine as a function, so f, this f, if you start with z and you replace z by e to the iz, so that is the map 5, f5, f5 takes z to e to the iz on this domain, on the same domain. So now we have e to the iz, and I want to multiply that by I. multiplication by I. So we'll call this dot I. So that's a function, multiplication by I. And then once I've multiplied by I, if I compose that with this map, -1/2. So maybe I'll put the I inside. Let's put this as -1/2 times I e to the iz plus 1 over I e to the iz. Does everybody see that? So I multiply by I, and now I have I e to the iz, and then I apply -1/2 z plus 1 over z to I e to the iz. So that's f6. And so what happens is sine of z takes this region to under f5. Under f5, it takes it to the half disk. Under times I, what happens when you multiply by I? Just rotates. Just rotates. And under f6, f6 takes this region to the upper half plane.
Isn't the above equation only true for z real?
Which one? Which above?
When you said e to the negative iz was 1 over e to the iz.
E to the negative iz, e to a negative power is 1 over e to a power.
Oh wait, no, sorry, I didn't have breakfast.
No worries, no worries. And the I moved to the bottom to make the minus sign a plus sign. So hopefully you can see that these functions we were building up to a very simple way of seeing what the sine function does. And it's that it takes this region, and we can color it in if we like to remember what happened. This part went to this part. This part went to this part, which got rotated, which got sent to -1, 1. This part went to this part, which got rotated and sent over there. And finally, this part goes there, goes there, and goes there. And that, ladies and gentlemen, is the sine function. So this to this is the sine function that takes this region to the upper half plane. Cool? All right, let's take a 5-minute break. Okay, so where were we? So we've been having fun with these maps, and now let's get a little more serious. So here's the observation. So if we have a map F from, let's say, U to the disk, just to pick some concrete place to work, what other are there others? Are there other conformal maps? How unique, if we have a map from some region to the disk, how unique is it? Well, if I don't want to say F prime, if F1 is another, then if I take F prime inverse, that goes from the disk back to U, and I compose that with F, that's a map from the disk to the disk. So, F composed with F1 inverse is an element of the automorphisms, the automorphism group of the disk. So this is the set of all functions from the disk to itself that are bijective holomorphic. And these form a group because if f is there, f inverse is there, the function f of z is z, the identity is there, which doesn't do anything to the disk. And you can compose two because they have the same domain and range, and they're all bijections. Okay, so this forms a group. This is the automorphism group. And so our next task is to understand this automorphism group. If we understand the automorphism group, then we know, okay, if I have two different functions, they differ by an automorphism. And so here's exactly what they differ by. And a key step in understanding the automorphism group is the so-called Schwarz lemma. This is the famous Schwarz lemma. It says the following: let f be a function from the disk to the disk, but I don't assume yet that it's bijective. Okay, all I assume is that the image is inside the disk, be holomorphic, not conformal, not yet conformal, not necessarily conformal. Okay, and assume, let's say it fixes the origin. So whatever it's doing, whatever f is doing, it's going from the disk to the disk, but the origin moves to the origin. F of 0 is 0. Okay, then we can already say quite a lot. Then, first of all, for all z in the disk, the image is no bigger than z itself. Second of all, if you have a single point where this is an equality, then f is a rotation. i.e., f of z is just some constant times z where the constant has absolute value 1. Right, so it's e to the I theta. So certainly rotations are automorphisms of the disk, and they have, every point has the same magnitude as it used to. So if there's a single point that has the same magnitude as it used to, all the points have to have smaller magnitudes than they used to. And if there's ever one that has exactly the same magnitude as it used to, then f must be a rotation. And third of all, what we know about the derivative of f at the origin is that it is also at most 1. And moreover, if the derivative is 1, then f is a rotation. Okay, does that make sense?
Z0 non-zero.
Sorry?
Z0 needs to be non-zero in part 2.
Z0, thank you. Except at 0. At 0, of course, it is equal to its own size. Okay. Let's prove 1. This is very simple. These are all the maximum modulus principle in disguise. Proof of 1. So if we expand f about 0, so f of z is equal to f of 0 plus f prime of 0z plus higher order terms, a2, z squared, and so on. The assumption was that f of 0 is 0. And if I divide this by z, I get a nice holomorphic function. So this is holomorphic. In other words, f of z over z has a removable singularity at the origin, has removable singularity at 0. Okay, so let's call this G of Z. So it's holomorphic on the disk. Holomorphic on the disk. Okay. So what I claim is that if let's look where Z has absolute value exactly R. So let's look at G now. I want to know what G does. G takes the disk. I don't know where it takes the disk. Okay, because I've divided by Z, so I'm doing something. If Z has absolute value R, so here's Z, it has absolute value R. What can I say about G of Z? G of Z in absolute value. Well, this is F of Z over Z. I mean, this is inequality. Now, F of Z, F is a map to the disk. And because you're mapping to the disk, you're in an absolute value. This implies F of Z in absolute value is less than 1, right? That the image is the disk. And so F of Z has absolute value at most 1. Z has absolute value exactly R. And so something of size R, so here's size 1. Something of size R under G must be mapped inside the disk of size 1 over R. So this is 1 over R. If you're on the circle of size R, then your image, I don't know where it is, G of Z, but it's inside a circle of radius 1 over R. Okay? And this is true. So let's get a little room. So this is true for all Z on this boundary. So G of Z restricted to the disk of radius R, or the boundary of the disk of radius R about Z, about the origin rather. About the origin. In absolute value is bounded by some number. So by the maximum modulus principle, in the interior, it's strictly smaller. So the maximum modulus principle tells us that G of Z on the disk of radius R about 0. Well, unless G is a constant. Okay, but even if it is a constant, it's bounded, let's say it's bounded by 1 over R. So every point in here is contained inside this disk of radius 1 over R. Does that make sense? So this point, now here's the funny thing. So now send R to 1. This point Z, it's in a disk of radius R, but it's also in a disk of radius slightly bigger than R, which means that its image is in a slightly smaller range. But it's also in a slightly bigger disk, whose image must be in a slightly smaller range. So that means G of Z on the entire disk is at most 1. Does everybody see that? If you're on a disk of radius R, your image is bounded by a disk of radius 1 over R. But not just on the disk, inside the disk, you're bounded by 1 over R by the maximum modulus principle. But now take R bigger and bigger. You didn't move. You're still at Z, wherever Z was. But you're inside every radius disk, and the image of every radius disk is inside a radius 1 over R disk. So the range where you're allowed to be is shrinking and shrinking until you can't be anywhere but the disk. Okay? And of course, G is F of Z over Z. So that implies F of Z is bounded by Z. So that was part 1. Part 1 was that F of Z is bounded by Z. So far, so good? Part 2, what if there's a point in the disk where G is equal to its largest possible value. So proof of 2. If there exists a Z0 in the disk, not at the origin, well, if there's any value where G of Z0 has absolute value 1, and that's the boundary, and that's the value at the boundary, then G is constant. And if G is constant, then F of Z is that constant times Z. And that constant has absolute value 1. And G of Z0, which is equal to C, has absolute value equal to 1. So F is a rotation. Cool? Okay. And part three. So we know what G of Z is. G of Z is F of Z over Z. I want to know what happens to this as Z goes to 0. Notice that this is also equal to F of Z minus F of 0, since F of 0 is 0, divided by Z minus 0. So what happens to this as Z goes to 0? This converges to, yeah, F prime of 0. Everybody sees. I mean, this was already obvious here, right? G, we divided by Z. So G is G of 0. G of 0 is F prime of 0. And G is bounded by 1 everywhere. And G of Z is bounded by 1, which implies F prime of 0 is bounded by 1. So that's the first part. Now, what if F prime of Z is equal to 1? If F prime of Z 0, F prime of 0 rather, if F prime of any point, including the point 0, is equal to 1, then G of 0 is equal to 1. And we have the maximum modulus principle, and we have the maximum modulus principle that tells us that G is a constant. And so F is a rotation. Cool? So this super easy theorem to prove, I mean, it's a little lemma, this little Schwarz lemma. It's super easy and it's incredibly powerful. Those of you that are starting to study for your qualifying exams, this will be on the exam. There is no qualifying exam that has not used the Schwarz lemma. So let me alert your attention to the fact that this is a key thing that pops up again and again and again. And it pops up again and again and again because it's so simple and it's so powerful. It's such a powerful idea. It will allow us, I guess not today, but that's okay. It will allow us to understand the full automorphism group rather easily. Okay, so any questions on the Schwarz lemma? So far, so good. Let's understand, I don't have time to go into SU11, but I will talk about it next time. Let's understand the Blaschke factors. If you recall, so we're back to trying to understand the automorphism group. There are these things called the Blaschke factors. This was on your homework long time ago. Blaschke factor maps. These are maps of the following form. So let's call it psi alpha. If alpha is a number of absolute value less than 1, psi alpha takes Z to alpha minus Z divided by 1 minus alpha bar Z. Now this looks like it comes out of nowhere. This was in your homework, this map. There's a very, very good reason for this map to exist, which is what I want to explain, but not today. This is a fractional linear map. How would we describe it as a matrix? humor me. Someone please read it off.
-1 alpha
Alpha
minus alpha bar 1.
minus alpha bar 1. Okay. A couple of things about this map. So first of all, let's see what it does to Z. Okay. So if we, let's see, how should I put this? Alpha has absolute value at most 1. I claim, so my claim is that alpha is an automorphism of the disk. It sends the disk to itself. And is holomorphic and bijective. Holomorphic and bijective. i.e., each of these phi alphas are elements of the automorphism group of the disk. And in fact, they're nearly the whole thing. That's what we're going to prove with Schwarz. In fact, okay, I maybe since I gave it away already, there's a theorem, which is what we're going to prove, that any automorphism of the disk is an e to the I theta. It's a rotation times the Blaschke factor. Okay, but we're going to come back to that. And this general thing, okay, this is what I want to talk about, but I don't have time, and so I'm throwing words at you. It's almost SU11, really P SU11, and really the extension. Okay, never mind. Next time we'll have time to really talk about this, both of these things. Let's see why this phi alpha maps the disk to the disk. Okay. First of all, is it holomorphic? So here's my claim. I'm proving the claim. Proof of claim. Okay, is psi alpha holomorphic? Well, where does the denominator vanish? Pole at 1 minus alpha bar z equals 0. In other words, z equals 1 over alpha bar. So the absolute value of this, alpha has absolute value less than 1. 1 over alpha bar has absolute value bigger than 1. So it has a pole outside the disk. So the pole is outside the disk. Okay, so it is holomorphic in the disk. Is it bijective? Is it bijective? So what's the inverse map? You can read it off the matrix. I switch these two. I switch these two. I negate these two. That's the inverse map. But remember, this map is only defined up to, it's really PGL2 that acts on fractional linear transformations. So I can multiply through by any constant. So I can multiply through by the constant -1. If I multiply by -1, I get 1 alpha, negative alpha bar, -1. Sorry, did I not flip the, I didn't flip the diagonal entries. I didn't flip the diagonal entries. Sorry, I'm supposed to flip the diagonals, negate the off diagonals. Flip the diagonals, negate the off diagonals. So now that -1 is supposed to turn into a -1. This is supposed to turn into a +1. And you're supposed to see that it's its own inverse. These things are involutions. So phi inverse, psi alpha inverse is psi alpha. So each psi alpha is an involution. Okay. Why does it, so it has an inverse, it's holomorphic, it's bijective. Well, as long as, I guess, does that already mean that it's onto the disk? I guess so, because if it takes the disk to some other region, and then it takes that region.
We could take the disk to like the disk with half the radius and then map that back bijectively.
No, but it's the same map. You
Oh, yes, never mind. Yep,
its inverse is
yep.
itself.
Yeah,
So
okay.
if it took a disk to a disk with half the radius, it would take the disk with half the radius to the disk
Something else.
to something else, right? Because it's the inverse map. So I guess that already means that it's that it maps the disk to the disk. But you can prove it directly. Maybe I'll leave it as an exercise since I'm out of time. Exercise.
I think we did that exercise already.
I think
on
you
that
did
homework.
this exercise already. Yeah, there's a bunch of stuff on the homework that I've been building up to. Like we've seen a lot of Poisson kernels and things like this that we haven't discussed in lecture. There's reason for it. So we will need these things. And now we need the Blaschke factors. So exercise, which you already did, but you can look back on it. It does indeed map the disk to the disk. And it is its own inverse. And let me just do one more thing. Yeah, let me do one more thing since we're out of time. A fact is that psi alpha takes 0 to, where is psi alpha? Well, we can read it off here. 0 plus alpha divided by 0 plus 1. It takes psi alpha to alpha. And since it's its own inverse, it takes alpha to 0. All right, and we're going to play with these Blaschke factors a lot more next time and see what they have to do with this Lie group and use the Schwarz lemma to use the Schwarz to see that the entire automorphism group can be described. I'm sorry, you're right. It can be described as rotations and Blaschke maps. Okay, so see you on Friday.